my great pleasure to introduce Tanja Kovačević. She's going to talk about mixing matters, revealing rock ice miscibility in massive water work. She's a grad student at UC Berkeley. She's working with the Burkhard Litzer, and she is NSF graduate fellow as well. And she has done outstanding work, and I cannot wait to hear about her work. So please take it away.
Yeah, thank you so much, Farhad. That was a very nice introduction. Thank you, I appreciate it. So yeah, today we'll be talking about the rock ice mixing in massive water world. So a little bit of foreshadowing that we're probably going to see some rock ice mixing within water worlds. So my name is Tanja. Farhad already kindly said I work with Burkhard at UC Berkeley. This is going to be the outline of my talk today. Here, let me get my laser pointer. So we'll begin with a little bit of background. I want to set up the motivation to investigate this rock ice mixing. Then I'll go over a DFT-MD that we performed to investigate the rock ice mixing and what pressures and temperatures are necessary and if they're relevant to exoplanet interiors. Then I'll discuss giant impacts or these impact simulations just to determine whether the mixtures, once we figure out the pressures and temperatures, whether these conditions are even found within water worlds, maybe post-impact. And then I'll finally conclude with a summary of the findings, and then I'll have a ribbon at the top that'll kind of keep us on track with where we are in the talk. So for example, here we are in the background. So these are the two papers, the results that I'll discuss from these two papers. So the first one I published maybe a year ago, the miscibility of rock and ice in the interior of water worlds. All of us were authors. We collaborated with Sarah Stewart. And then the recent paper I just published like a month ago on the homogeneous mixing of MgO and H2O. So I'll discuss those two results. That was just with us three, so Burkhard and Felipe. And that was published in Contributions to Plasma Physics. So let's begin with a little bit of background. So the first exoplanet was detected in 1992, and planetary science has been kind of booming ever since. So that satellite you just saw rush across the slide have been able to discover thousands of exoplanets. And they are able to provide these mass radius relationships for these exoplanets, of course, with varying degrees of uncertainty. And currently right now, our technology is a little biased to the close-in planets, or those are the ones that kind of have been confirmed. So meaning that they have super short periods because they're super close to their host star. And so those are kind of like the planets that we have to work with. In 2007, Sarah Seeger, and then Burkhard was also on the paper, made this mass radius plot that some of you might be familiar with. So they found that all we needed to characterize the bulk composition of exoplanets were relatively well approximated equations of states for common planetary building blocks. So let me tell you how to read this plot. So we have mass on the x-axis, and this is just a log-log plot. So this is like, if you look at m over m Earth, one corresponds to, it's just like one Earth mass, 10 Earth masses. So this was kind of translated to make it easy to read. And then we have radius on the y-axis. And then if we plot an equation of state, so let's pretend we have a planet that's 100% iron. We can plot the equation of state, so how the mass and radius would change if they're both increasing, like let's say the mass is increasing, how the radius changes as a function of that. And then we can just plot the exoplanets we found. So back in 2007, we didn't have a lot of exoplanets. So those are those pink ones, but we have our solar system planets here. And we can kind of see, we got some like maybe gassy planets. The terrestrial or rocky planets are located a little lower on this plot. So from there, we could categorize these exoplanets that the space satellites were finding. And we have a couple types of exoplanets. We have terrestrial, super Earth, sub-Neptune, and gas giants. So the easiest thing to do is look at these categories and compare them to our solar system. So we have terrestrial planets, so Mercury, Earth, Venus, and Mars, for example. And then we have gas giants, like Jupiter and Saturn. Sometimes Neptune and Uranus are thrown into the gas giants, but they're can be referred to as ice giants as well. So kind of, Uranus and Neptune would fit kind of in the in-between here, and then Earth would fit kind of in the in-between here. But some of the most common type of exoplanets, the super Earths and sub-Neptunes, we don't have an analog in our solar system. So that's interesting. Let's focus on these exoplanets. Fulton in 2017 plotted the distribution. So the exoplanets that we had that they kind of filtered them a little bit just to look at certain exoplanets. So ones that were certain sizes, so up to Neptune size, they plotted it with respect to Earth radii. And you see that there's kind of like these two bumps here. So that's called a bimodal distribution. And that means that the occurrence of these planets, it seems like there's two types of planets that like to occur. That when, I guess, the planetary system is being formed. You're going to have planets that like to be around 1.3 Earth radii and around 2.4 Earth radii. So this is famously known as the Fulton gap. There seems to be like a gap here where there's a dearth of exoplanets. So if we think about our solar system, let's add some vertical, I'd like to add vertical lines to like remind us the size of Earth, which is the green dashed line, and then the size of Neptune, which is the blue dashed line. So this plot is kind of helping it make it more evident that Earth and Neptune kind of lie outside of this distribution of like where planets like to be sized, it seems like. Again, there could be like a lot of reasons for that, but it props up the question, why don't we have one of these size planets in our solar system? So back to Fulton's paper. Ultimately, what they concluded from that paper was that once planets get to a certain size, so once they kind of get, sorry, my mouse, once we kind of get to this edge here, the planet quickly begins to attract hydrogen and helium to form this gaseous planet. So these sub-Neptune-like planets, while the smaller ones can't really hold on to an atmosphere. And then they're going to remain primarily rocky. Another conclusion from this was that maybe the smaller planets could be the cores of sub-Neptunes and they just had their atmosphere stripped away. I also mentioned that previously on a slide or two ago that Uranus and Neptune are also referred to as ice giants, and water is an abundant planetary forming material. So out of the ices, water is readily abundant. So we could also ask, what about the water content in these exoplanets? This plot, unfortunately, isn't sensitive to planet composition. So while it was a really highly influential study, to kind of determine and refine the methods to resolve the differences, we need to get a little more detailed so we can tell what interior compositions of these exoplanets we're seeing are. So if we remember back to 2007, that mass radius plot that I shared with you, we could use it to infer bulk composition. So let's use an updated, much more complicated mass radius plot. It kind of shows that we're trying to move in that direction of trying to understand the interiors of these planets. Yeah, the plot gets a lot more complicated. This is a really good paper by Zhang and others in 2022 that was published in PNAS. So if you want to go back and read that paper, this plot is really cool. It takes a little bit of time to understand, but I'd like to just take a closer look at this portion of the map. We still can't really tell between, this plot isn't really going to give us oh, there's this much water in this planet and these planets are, it still doesn't give us totally an exact idea of what the interior composition of the planets are, just this, again, bulk composition. But based on, in this paper, Zhang ran growth models and they conducted these Monte Carlo simulations. So in 2022, and they provided evidence that these intermediate sized planets, so here, are going to be water worlds. So this red line I kind of put in there to indicate that's where they kind of capped where these pretty much beyond that, if we go up in radius, we're going to require the presence of a gaseous envelope. So they kind of made the statement here that there's some evidence that some of these planets, exoplanets, are water rich. We can maybe look at mass versus density instead. So that's what Luke and others did in 2022. And they provided a little bit more evidence, a different type of evidence that there are some water rich planets. So this kind of light blue line is showing where water would begin to accrete. And then the dark blue line is showing kind of where gas begins to accrete. So this is some more evidence that there's kind of like the presence that we have that we potentially already found some water worlds. Even JWST is looking for atmospheres of various exoplanets. And a couple months ago, NASA showed like those preliminary results and showed that there might be water in the atmosphere of the planet WASP. Oh, the text is kind of tiny here. WASP 96b. So we're looking, and even like new proposals for JWST are looking for water worlds. There was like an ESA report of sending a mission either to look at water worlds or to look at Uranus and Neptune to understand their interiors. So I hope I've been able to motivate the interest in water worlds and provide some evidence that maybe we already discovered some water worlds. We just can't really distinguish them quite yet. So the reason that I'm interested in these like water-rich planets isn't just because of the propensity at like which we find them. I mentioned water content in the last couple slides, mentioned it when I was talking about the Fulton gap, that like water is pretty important, and we know it's a common planetary building block. So to offer a couple more reasons why we're interested in these water-rich exoplanets, let's tabulate a couple of things we know. So Earth hosts life, and water is necessary for life, at least as we know it. We know plenty about the interior of Earth, but the interior of Neptune is much less clear. So I think that these are also some other great examples as to why we would research water worlds, even though we can't quite distinguish them yet in our mass radius plots or like, you know, kind of the ways we're analyzing them. It'll still take several years, but again, I believe that there's enough evidence that they exist out there, and water is so abundant that, yeah, hopefully I'm just trying to convince you of the story I have in my head. So now that, you know, we're really on this water world hype, I'd like to build a simple picture of what the interior of a water world may look like. So let's begin with the definition for a water world that we'll use for the rest of the presentation. A water world is a planet of rock and icy composition without a significant atmosphere. So this is just like our way of cheating a little bit. These calculations that I do are pretty expensive, and they're pretty complicated already with the amount of elements, different elemental species we have in them. So like without the significant atmosphere allows us to not think about hydrogen and helium for now, while we're still figuring out like other things. You know, we got to start somewhere. So we're not going to have an atmosphere. We're just going to be thinking about rock and icy compositions. So if we go from the interior to the exterior, we're going to start with an iron core. We're going to have a rocky mantle, and then these huge water layer overlaid. And this planet is differentiated, meaning that all the layers are separated nicely. And that has a lot of like baked in assumptions about the planet's formation and evolution. And then with this massive water layer, the pressure and temperature conditions at this rock ice boundary would be pretty large, at least compared to like on Earth, where we have like less than 1% by mass like of water on Earth. This is a lot of water. So these pressures and temperatures are going to be pretty extreme. And then if we look at like other planets in our solar system, we're starting to begin to understand or maybe theorize that planets are a little more fuzzy than we'd like to believe. So why not think the same with the interiors of these water worlds? You know, use the most state-of-the-art data that we have and methods that we have. So what are the implications? So, okay, cool. If rock and water are mixed inside these planets, what are the implications of that? So in 2022, Alana Vassan asked the question about a mixed water world interior. And she investigated in that paper the thermal evolution of water-rich exoplanets. However, because there weren't any rock ice mixing simulations or calculations done or experiments done to determine whether rock and ice mix, she made the assumption that beyond the secondary critical point. So a secondary critical point is pretty much where you have two materials where they mix and you can't tell them apart. So she assumed that beyond that point, rock and ice should mix in all proportions. And from that paper, with this thermal evolution stuff, they were able to determine, and they theorized, that rock and ice remained mixed for giga years, and that ice water content of a planet, which was interesting for me, couldn't be inferred from the atmosphere alone. So I mentioned how JWST is looking out at exoplanets for the atmospheres to see if there's water content, that like maybe we have to think of some other ways to determine the water content within these planets. But let's just say for now, these rock ice mixtures will last for a long time, and that there may be a large fraction of ice in the interior of these water worlds. Then even before that, this was like, I was already well into the project. I kind of, saw this paper a little later, even though it came out before, but it kind of opened my eyes. So rock ice mixing even has implications for magma ocean worlds. So Carolyn Dorn and Tim Lichtenberg in 2021 investigated how water sequestration into rock affects a planet's radius. So, whether there's no mixing, there's this dry melt solid interior, or whether there's like full mixing of the water into the rock. So, okay, cool. I pretty much said that the water can hide inside these rocky materials. It'll change their evolution, their thermal evolution, which is like important for us. But why might water hiding be important for, research and understanding, these mixtures, and why it might be important for planetary science is that in 2021, Edwin Kite actually suggested that water hidden within terrestrial planets that were once sub-Neptune. So remember, I said Fulton made that hypothesis that like some of these super Earths could have just been sub-Neptunes that had their atmosphere stripped. That these once sub-Neptune, now like super Earth-sized planets could produce water-dominated secondary atmospheres, which, very important. And just in general, a rock ice mixture is a new material, and the material and transport properties are going to differ from rock and from water alone, and they're crucial to understanding the planet dynamics and evolution. So hopefully I've been able to provide lots of evidence that there might be exoplanets out there. I've given implications and really motivated the work. So I hope we're all on board as to why we're studying water worlds and why I'm interested in rock ice mixing. So why not ask the main question of the work? Are rock and ice miscible at the rock ice boundary layer deep within water worlds? And by miscible, I mean the homogeneous mixing of two substances. So I might say miscible, I might say mixing. Those are interchangeable. I also might say water and ice interchangeably. I'm still kind of confused about like the regime that we're in. When my water melts, it's it's kind of like dense water, because it's like it's dense ionic water. So it's I kind of use ice and water interchangeably, maybe a little egregiously, but just a forewarning. Okay, and then in my group, since you already saw, I kind of mentioned DFT-MD simulations. That's what we use in our group to investigate mixtures, and it's been used to investigate mixtures such as iron and MgO, hydrogen and water, hydrogen and MgO. So again, being part of Burkhardt's group, I'm a little biased to say that I believe the DFT will work to investigate these rock ice mixtures and give us an idea what the conditions are necessary for mixing. So let's start by preparing our simulations. First, we're going to need to pick materials of interest. So I mentioned those two papers where I discussed MgSiO3 and H2O mixing and MgO and H2O mixing. Now I'll focus just on MgO H2O mixing when I'm showing the results, because both methods were done like very similarly. So I don't want to be redundant, and I'll show you the results from both papers a little towards the end of this DFT section. So, okay, we picked our materials of interest. Now we need to begin choosing conditions to investigate. So here's a pressure and temperature plot. These are the conditions that we chose to investigate. So we just, using our hydrostatic equilibrium equations and some mass conservation laws. And in our group, we calculate equations of state. So we have equations of states for materials at the ready. I can build planets, very simple with not much physics in it, but it gives us an idea of what the pressures are that would be at the rock ice boundary. So that's how I got the pressures. And then the temperatures that I picked were just to make sure that all the materials melt in my simulation. So that was just a goal. Now, I've picked the pressures that I think are going to be of relevance. Now we just need to make sure there aren't any high pressure rock ice, like these hydrated silicates at these conditions. So we went ahead to check that. And you see, in 2013, 2014, there was some hydrated silicates found in this blue region, and then some ultra high hydrated, I think it was like ultra high hydrated magnesium silicates found in 2022. So this is all stuff that's like, it's like very recently coming out. And we're going to be in this nice sweet zone where we still have the rock and the ice phase separated. Now, the next step, we're going to have to build. So we have our materials, we have the conditions we want to investigate. So we need to build our cells. So an approach we're going to use is going to be a heat until it mixes approach. It's going to overestimate the mixing temperatures a little bit, but we still think we argued in the paper the reasons why we believe it'll constrain this heat until it mixes will constrain it pretty well. So, you can ask questions if you want, but I'll just kind of keep moving on so I can keep my talk on schedule. So next we build the supercell. So we know what our rocky material is. We know what our ice is going to be. So we're going to go ahead and, get those crystal lattices and build them. So we have the rocky material on the bottom, ice on the top, and all the atoms are colored as such. I just want to make sure to point out that the rock oxygens and ice oxygens are colored differently. This just helps with visualization purposes instead of just having like red atoms everywhere, and then also helps with some analysis that we're going to do soon. So I have my system. I'm going to build 2 more. So this system is the one that's relevant for 120 GPa for system 3 that I'm showing you here. So I have the crystal lattices for bridgemanite and water that are going to be relevant at 120 GPa. And I do the same for these 2. I relax the systems before I begin. And then I'm going to run simulations where I increment the temperature in 500 degrees and run simulations all the way up to 8,000. So that means I'm gonna have a lot of simulations, and we're just going to investigate. We're going to be able to produce isocores and investigate whether there are phase changes. So again, we're going to get on a pressure temperature plot, we're going to get isocores. So fast forward a couple months, and I've been able to calculate these isocores. And then we see that there are some kinks in the line, which is indicative of maybe some phase changing going on. Of course, that's just a qualitative view of this. So we're going to have to use some quantitative processing methods. And those 2 methods are fairly simple. We're going to use a mean square displacement, which is going to tell us how much an atomic species diffuses throughout a trajectory, given an initial starting point. And then the radial distribution function or paracorrelation function, they're interchangeable, is the probability of finding a particle at a distance r from another tagged particle. Again, for brevity and for time's sake, we are just going to look at the MSD results. And then even more refined, we're going to look at the MSD just in the Z direction. Because as we know from the definition, the MSD is going to give us an idea of how much the atom diffuses, an atomic species can diffuse throughout a trajectory, but that doesn't really give us information about mixing. Now, if we decompose this 3D MSD into just the Z direction, so up and down or perpendicular to that interface, that's going to give us maybe some idea of whether this material is mixing, and then we can go in with the RDF to confirm. But yeah, so that's, again, a caveat. We're just going to be looking in the Z direction. I'm going to remind you that as I discuss the plots that we're going to see in the next couple of slides. So quickly, I'll go with you how to interpret an MSD plot. So we're all on the same page before I just start throwing like tons of plots at y'all. So we have MSD plots where we're going to see some solid, and MSD plots that are going to indicate diffusing or mixing. So on the x-axis, we're going to have time, which is just the length of the trajectory. And then on the y-axis, we're going to have the MSD. So how much the atomic species has been displaced over the length of the trajectory. Now, each line is going to correspond to the atomic species. So I'm trying to, not have us do a lot of work here, keep all the colors consistent. I'm a visual person, so I like I's dotted, T's crossed. So let's look at the solid MSD. So if an atomic species, if its MSD has either a 0 slope or is close to 0, so if we were to zoom in here, we'd see a bunch of more colored lines. That's going to indicate that our system is solid. The atoms are vibrating around their lattice points, but they're not diffusing. Now, if the MSD is increasing with time, that's going to indicate diffusing and then give us an idea again about mixing, because remember, we're only looking in the Z direction. So yeah, it's going to give us an idea about mixing. Now let's jump into it. Here's my isochore plot that I've thrown back up there. We have a lot more points and a lot more colors. Right now, I just want y'all to look at, we have blue points and we have red points. So blue points are going to indicate no mixing and red points are going to indicate that there's mixing. Cool. Now, let's discuss what all those different shapes mean on that plot. So initially, let me take a step back. On the isochore plot, I'm highlighting all the shapes, all the same shapes, like with the green. So you can, if I say rock is solid, ice is solid, all of these that are highlighted are going to have rock being solid and ice being solid. And then this circled, I guess, highlighted circled little point is the actual MSD that we're looking at here. And we're going to have the temperature at what it's at the top. So again, all of the hexagons, green highlighted points are going to have rock solid, ice solid. We can't see the lines. Trust me, they're there. I just want to keep the axes the same. So they're there. Next, with these cross points, the first interesting high pressure phase we're going to see is superionic ice, which means that the oxygens are going to stay put in their lattice sites while the hydrogens are now like diffusing like water. So we see that with these protons. Their MSD is like shooting right off the page, like within a picosecond, it's like jumping off the page. And then again, the ice oxygens do shift a little because of all of the protons now like moving freely around. But again, the slope is 0, so they're going to be vibrating around those lattice points. Next, we have all the triangular points where we get to this like melted ice phase. So we still have rock is solid, but we get to this melted ice phase where again, it's not like water, it's not like H2O floating around, it's like this dense ionic liquid. So yeah, we see that the MSD is kind of slightly going up for these. Again, we're only looking the Z direction, so there's only so much area that like water can move in when we had the like rock and ice on top of each other. So it's a little, the behavior is a little subdued, the MSD is a little subdued, but if you look at it in 3D, again, you're gonna have to trust me. You can look at the paper, it is diffusing a lot more than what's shown here. And then finally, we get the pink points, which indicate rock and ice mixing. So I wanted to show you that right after we get past this point, we're going to see the mean square displacements for all the atomic species increasing with time, which is going to give us an idea about mixing. Now, instead of just going through and showing all the radial distribution functions, it's a little complicated to explain. I thought I could show y'all a video of the simulation of what we mean by mixing. So we start off with ice on top, rock on bottom. This is within like 3 to 4 picoseconds. We see that I'm having a hard time telling the difference between icy and rocky material in the simulation. And as it goes on, it just becomes more of this rock ice slurry. So if those MSD plots didn't convince you, at least hopefully this trajectory does. Yeah. So here are the results from the DFT-MD simulation. I have plotted the melting curves for both MgSiO3 and for water, just to kind of see what's going on, see if we can see any, I guess, yeah, see if we can see any, what's the word I want to use? I'm kind of blanking right now. But anyways, I also wanted to show you all my MgO H2O mixing results. So I did all the same steps as I just did that I explained to y'all. And we produced one isochore. So this was just a quick paper published in a contributions journal. And again, I have the water melting curve. I have the MgO melting curve. As you can see, the mixing happens. We're going to still have blue means no mixing. Orange now means mixing. We're going to see that well below this MgO melt curve. Now we have rock ice mixing. And just to kind of like see where we're coming from here, I plotted the MgSiO3 and H2O miscibility curve. So again, why I'm focusing on MgSiO3 is that it takes a little bit higher temperature to get it to mix. So again, if Sarah's results are showing that the temperatures are achieved for mixing, then we know for sure MgO and water will mix. But just quickly wanted to show those results. Now let's get back to the MgSiO3 and water mixing results. So I hope we can all see a relation that it looks like all it takes to get mixing for at least bridgemanite and water is that bridgemanite has to be melted And then these, the materials fully mix. Okay, cool, Tanja, you told me that the materials mix, but like, can we even find them within water worlds? Usually we maybe assume these planets might be a little cooler if they haven't, let's say, like migrated, or we still don't know a lot about, you know, how planetary systems form. So there's a lot to learn, but ultimately I kind of ask the question, cool, I know there's rock ice mixing, what now? Can we find them within planets? And that's where Sarah comes in. So a little preface to impact simulations. We're going to take a step back and think about the growth of a planetary system and how planetary systems grow from this kind of clump of gas just in space into something we're more familiar with, something like our own solar system, maybe. It's also another very active area of research. So I'm not going to say that like I know a lot about this area, but I'm going to use some of their models to my advantage. So I'd like to think about a particular model. Yeah, so let's look at that region of the solar system formation or planetary system formation. Many researchers who work in this field believe that like some planets grow through collisional growth. And that pretty much means that planetesimals, or like these mini planets, are colliding into each other and forming these larger planets. So kind of something similar to Earth. Yeah, just these giant collisions. Planetary growth is a violent time in a solar system's life. So we're going to use that collisional growth model to our advantage because they are highly energetic. And what is a more perfect source of increasing the temperature of these exoplanets than having them impact each other? So, and then we also have Sarah Stewart, who can run these impact simulations. So again, going to use that to our advantage. So for our impact simulations, we're going to assume that the water world grew through this collisional growth model. And here I just have a fun picture of like maybe some ice giants slamming into each other. So Sarah ran SPH simulation, or smooth particles hydrodynamic simulations. This is a collaboration with Sarah at UC Davis. She ran like a bunch of impact simulations where I've kind of quickly summarized the initial conditions here. This plot that we're seeing here is going to be kind of the end member cases. So, but again, we ran combinations of all of these types of planets. Again, you can see it in the supplementary to the MGSIO3 paper in the scientific reports. It has all the simulations tabulated, but she has 2 planets where we have an iron core, rocky mantle, and this huge water layer overlaid. So kind of going back to that initial 3-layer water world we were kind of thinking about. And then she's going to run simulations. I love showing simulations, and these impact simulations are like the coolest to watch. So yeah, she just centered the simulation on this planet, and we have a graze and merge event where 2 planetesimals become 1. We're going to look at the conditions here at the rock ice boundary. So we're not going to really care about the points out here. We're just going to look at this rock ice boundary and pool the thermodynamic data from those points. So pretty much I guess we filtered them for like pressure. So you have to have, you know, the material that's at higher pressure is going to be deeper within the planet. So from all of those simulations, we're able to get the pressures and temperatures of each particle and see whether the temperatures were met. I guess the pressures and temperatures are necessary for mixing for those particles. And that will give us an estimate of the rocky material that's mixed up into the water layer. So from all of those results, from all of those initial conditions, we were able to determine that anywhere from 6 to 22% of the rock is mechanically mixed up into the water layer. So kind of as I alluded to with my not very obvious title is that, yeah, the pressures and temperatures are totally reachable within these within this collisional growth kind of assumption we have for the way these planets grow. So ultimately, the conclusion of this work is that we now have provided theoretical evidence that many water-rich exoplanets have mixed mantles, and we'd like to just add this little additional brown mixed layer. Of course, it'd be a little more fuzzy, but just to give kind of like some visual takeaway is that, yeah, there might be mixed mantles within water worlds that we have probably already discovered. And yeah, this mixing and demixing, you know, with evolution has like implications on how a planet evolves. And like I mentioned, maybe secondary atmospheres. We have a lot to learn. So this field is still very bumbling. And yeah, ultimately, I'd like to thank everyone, all the collaborators, the Militzer Group, Sarah Stewart, colleagues that I've talked to that have helped me with the project and understand things. Obviously, CMEC and the NNSA for the grant money, and NSF and H2H8 for fellowship. And I wouldn't have been able to run all these calculations if it wasn't for all the time I get at Lawrence Livermore National Lab. So also thank everyone over there. And it looks like I was chatting pretty quickly. So it's good. I'm at 40 minutes. So yeah, thank you everyone. And thank you for inviting me to give the talk.
Thank you so much, Tanya. This is great. So now this talk is open for questions and comments. Either you write down your question in the chat or you can unmute yourself and speak.